let's run through an example. So we've got a function here. This is just some function. We're not going to worry about the economics of it yet. We're just going to worry about mastering our tool, which in this case means we're just going to throw ourselves into it and start taking derivatives. Once we've got those derivatives, we're going to go through the procedure that we discussed, where we're going to try and find out what's going on at the points we find using our derivatives. So zx, there's no x in there, so the derivative of that component with respect to x is 0. 0 minus, well, here we got an x, so we got minus 6x is our derivative with respect to x, minus 6y. Here we're treating y like a constant, so the derivative of this with respect to x is 6y. We've got no x in here, and we've got 72x here, so plus 72. zy, what have we got? We've got a 48. No y here, minus 6x, minus 4y, and then a 0. All right, so with this, we can find some critical points. Now, since we know that they're both equal to 0, let's see, how can I get rid of these? Those 6's would cancel. Yeah, so let's just set the two equations equal. So minus 6x minus 6y plus 72 equals 48 minus 6x minus 4y. Well, we add 6x to both sides. That cancels, and now we got something just in terms of y's. Let's add 4. This becomes minus 2y. Let's subtract 72. This becomes 48 minus 72. All right, so we got rid of this 4y. We dealt with that 6y. Negative 2y equals this stuff. So y equals, well, this is going to be something. What's it going to be? We're going to have a 4. All right, so 48 plus 4 gives 52, 24. Divided by, sorry, and actually this is minus 24. Minus 24 divided by minus 2 equals positive 12. All right, cool. So we've solved one part of our critical point. We might have more than one, but let's see. So we've got y equals 12. If we plug this into either one of these, let's plug it into this one, right? So I know that this is 0 at my critical point. So 48 minus 6x minus 4 times 12 equals 0. So that means 6x equals 48 minus 4 times 12. All right, so I'm really moving the 6x over and then flipping the side. So 48 minus 4 times 12. What is 4 times 12? That would be 48. So 6x equals 0. 0 divided by 6 gives us x equals 0. So our critical point is 0, 12. Great. So we got the first part of our problem. This is our candidate solution. This is the interesting point that we find from this function where things are flat in both dimensions. All right, let's find zxx. That's going to be minus 6, and that's it. zyy is going to be minus 4, and that's it. So, hey, that's pretty nice. And then zxy. What's that going to be? zxy, that's going to be minus 6. And let's just verify zyx is also minus 6. So we've got two negative second derivatives. What does that mean? Well, it means that we're at some critical point where we've flattened out and our derivative is getting smaller, which means as we move to the right, we're falling off the top of the hill, which means since we were getting smaller, we must have gotten smaller from something that was bigger. So we've got something hill-shaped, right? Which means we're looking at a local max in both dimensions. All right, so this is promising. 0, 12 looks like it's at the top of the hill. Now we've got to check that final condition, which is zxx times zyy, which is, what, 24, has to be greater than zxy squared, which it is not, right? 24 is not greater than 36, which means we've got something funny going on in the cross partial derivative. What does that tell us? Well, it tells us that this looks like a maximum, but basically as we move away from here, right, so we've got a point like this, right, at the 12, where it looks like it's flattening out in this dimension, it looks like it's flattening out in this dimension, but in the corners, we're getting more, right? So we're getting smaller, faster, but I guess, let's see, zxy. So what happens to zx as we change y? Let's think about that for a second. So we've got zx, right? How does this change with x? And let's just imagine we're thinking along the y-axis. So the slope of x with the slope of z with respect to x, holding y as a constant at our candidate point is 0. So we got something that looks like it's flat in this direction. And we're asking, how does that change? How does this slope change, which, you know, could do any number of things as we move? How does that change as we change y, right? So how does this change? So this is, you know, at any given point, this is what's going on. And so this condition we're checking, is it at the top of the hill, right? Is it doing this when we look at it from one particular direction? But if, as we go off in the corners, we go from something like this to something like this, you know, instead of, you know, the other direction, well, let's do this. Let's go ahead and load up Wolfram Alpha, and we'll see what it looks like. So our function is, we will 3D plot the function 48y minus 3x squared minus 6xy minus, whoops, where's my minus? Minus 2y squared plus 72x. All right, let's see what it looks like. And we'll try and make sense of this cross partial derivative. So here we can see 0 and 12, right? So we've got this point that we're looking at right here. And we can see that it's getting higher as we go up and to the left or down and to the right. So although we can see that along a slice of the x dimension, it looks like a parabola, and a slice along the y dimension, it looks like a parabola that's opening down. In fact, if we were to rotate this, right, if we imagined, let's call it dimension y prime, and this will be x prime in this direction, in this case, x prime is a downward parabola and y prime is an upward parabola. So this kind of looks like a sort of a saddle point from that direction. I guess technically this is a three-dimensional, a three-dimensional inflection point. Whatever the case, it is certainly weird. And it is certainly not an actual local max, even though it looks like it when we look at just the second partial derivatives. So let's go back to our notes and walk through this. We started with some function, some three-dimensional function where z is a function of x and y. We took a bunch of partial derivatives, second partial derivatives, cross partial derivatives, and mechanically, that was just the same sort of stuff we've seen with regular derivatives. We're looking at a nicely behaved polynomial, so it's nothing terribly complicated to actually do the math. The hard part, as always, is in the interpretation. So we go through this. We set these equal to 0 to solve for this critical point. We find this critical point at 0, 12. And in this x dimension, right, it's roughly parabolic. And in the y dimension, right, so let's imagine we're looking at this from, well, whatever. We'll say from this direction. I'm going to try and draw a backhand, right? It looks, again, parabolic. So it looks promising for this by checking these second conditions, but this final condition where we ask, does the effect of this parabola and this parabola outweigh the effect of whatever's going on in the opposite direction in the corners? In this case, actually, sorry, these corners go down, but these corners go up, right? And we get that because zxy is bigger than, well, zxy squared is bigger than zxx times zyy. Right, so given that, we don't actually have that maximum. We have an inflection point, which in this case, it's not a super exciting inflection point, but all that really boils down to is there's a change in the shape going on. There's a change in the change of the slopes around this point, such that although this is getting smaller when we go north-south and smaller when we go east-west, that is not true when we go in another direction, like northwest or southeast. All right, so that was an example of three-dimensional optimization. In this case, we didn't find an optimum, but we found the critical point and we found out what was going on at that critical point.